So let's look at the formal definition of a limit. What I want you to do is I want you to consider this function here. F of x is equal to 2x plus 1. That's a normal, nice, straight linear function. Okay, it's an easy function to deal with. Now we're going to consider the following limit. The limit as x approaches 2 of that function. So the limit as x approaches 2 of 2x plus 1. And immediately in your mind, now that I showed you how to solve limits, you can work this out. You know that just substitute 2 in. Is it going to give you a problem? Absolutely not. It's just a linear function. Sub 2 in, you'll get 2 times 2 plus 1. It's equal to 5. So you know in the back of your mind already that the limit value is 5. Okay. So we know that as the x variable approaches 2 from the left or right, that's what we mean when x approaches 2. Okay, it's approaching it from the left or the right. The y variable of the function, which is the output value, will approach 5. And we solved that. We solved it by inspection. We just have to look at it. So let's actually illustrate this in the table below. And why I'm doing this is I'm going to show you how the formal definition of a limit is arrived at. So let's look at the table first. In the first row here, I have x values. So I'm looking at x is equal to 1, 1.5, 1.75, 1.9. So you can see that these x values are approaching 2 from the left. If you had to look at let's draw a number line. Here's 2. You have 1 here. 1.5 is somewhere here. 1.75 is here. And 1.9 is there. So we're approaching, here's the value of 2. We're approaching it from the left. We are on the left-hand side of 2 and we are approaching it. Okay, so why am I doing that? Because I'm looking at x approaches 2. That's why. Okay, and then if we look at the right-hand side of the table, we're starting with 3. X is equal to 3, then we're going for 2.5, 2.25, and 2.1. So now we're approaching 2 from the right-hand side because we're on the right of 2, we're at numbers greater than 2, and we're moving downward toward 2. So we are approaching it from the right. Okay, and then what I have in the second row is 2x plus 1. That's basically y values, that's output values. So sub 1 into this function, you'll get 3. Sub 1.5 into this function, you can try it out on your calculator if you need to, you'll get 4. Sub 1.75 in, you get 4.5, and so on. Just take a minute to look at these y values and notice their pattern. Okay, so let's look at the pattern. As we approach 2, so 2 is here, somewhere in the center. But remember, since we're considering limits, I'm not concerned about the value at 2. I'm concerned about approaching 2 and checking what the limit is. I'm not concerned about what is actually happening at 2. So we are going to approach 2 from the left. Your x values are going to approach 2. Look at your y values, 3, 4, 4.5, 4.8. It looks like they are approaching 5. And then let's look at what happens when we approach 2 from the right. So 3, 2.5, 2.25, 2.1. X values are approaching 2 from the right. Let's look at what happens to the y values. 7, 6, 5.5, 5.2. It looks like we are approaching our limit value of 5 that we suspected or that we calculated using inspection. Okay, so these values are approaching 5, and that's the y values. And that's how this table essentially works. Okay, so take a minute to look at that. Now, I want to do something with the table. Okay, let's look at the values of 1 and 3. So we're going to look at these ones because they're not fractions, they're just nice numbers 1 and 3. Let's assume that x is between, okay, let's assume that x is between 1 and 3. But, so we're going to say and x is not equal to 2. Why am I saying this? Because again, we are concerned with limits. I do not care about what is actually happening when x is equal to 2. I'm not concerned about f of 2. I don't care about this, substituting 2 into this function. So that is why I'm saying x not equal to 2. I'm concerned about what happens when x approaches 2, not when it equals 2. So I'm concerned about all of these values here, not when x equals 2 exactly. I'm concerned about all the other values approaching 2. Okay, so we have that. Let's get this out of the way. So we're assuming that x is between 1 and 3, and x is not equal to 2. What does this mean for the y value? So this all is going to imply something. Let's make some space. There we go. Okay, so this is going to imply something. What does that mean for the y value? It means, so the y value is between 3 and 7. Here's your y value in the second row. So if I choose any x value between 1 and 3, and I'm not choosing 2 exactly, what's the y value of the function going to be? It's going to be trapped between 3 and 7. You can't get an answer, a y value of 10, because take any number between 2 and 3, 1 and 3, don't choose 2, and sub it in that function. You're never going to get an answer of 10. Okay, so what we can say with certainty is that the y value is going to be trapped between 7 and 3. But how can I write the y value of a function? Another way of writing the y value of a function is f of x. So what I can say now, let's get this out of the way, is that when x is between 1 and 3 and x is not equal to 2, then the y value, or the output value, or we can call it f of x, is going to be between 3 and 7. Okay, so that's what we have here. Now, I want you to take a look at this implication. And what I'm going to do is I'm going to write it in another form that's a bit neater. So I'm going to write it in this form. This is the exact same thing. I'm going to say the absolute value, x minus 2, is greater than 0 and less than 1. And that is going to imply, so this portion here is that portion there. Okay, before I go on to the second portion, let me explain why this is the same. So what I said was that this portion here is the exact same thing as that. Let's look at why. So the first thing I want to do, if you look at this, it's actually two inequalities. We have the absolute value of minus 2 is greater than 0, so that's this little part here. And we also have the absolute value of x minus 2 is less than 1. If you put them both together, you get that on top. So let's look at this first part. Let's think about this, what this means. The absolute value of x minus 2 is greater than 0. Now, we already know that the absolute value of anything is always going to be a positive number. But there's one little peculiarity. What happens when that is 0? Okay, then it's not positive. So there is a condition here that is being applied. So if this output is always positive, okay, it's always going to be positive. It's always going to be greater than 0. But there is a specific condition that we need to deal with. What happens, okay, if that is equal to 0, then we're going to have the absolute value of 0 being greater than 0. And we cannot say 0 is greater than 0. Okay, this is incorrect. So that's the condition we need to deal with. When whatever is inside the absolute value is equal to 0. Okay, it's supposed to be 0 is equal to 0. That's a correct statement. We can't say 0 is greater than 0. That's crazy. Okay, so what we are saying with this here is we are actually saying that whatever is inside the absolute value cannot be equal to 0. Okay, because if this is equal to 0, then we're going to get the absolute value of 0, and we'll get that crazy statement, 0 is greater than 0. That's nonsense. Okay, so what we need to do is have this restriction. So x minus 2 is not equal to 0, and then we just solve. Wow, look at that. That is what we had there on top. X is not equal to 2. So by saying that the absolute value is greater than, the absolute value of x minus something is greater than 0, we're actually taking care of that restriction. We're taking care of the restriction where we want to look at x at that specific value that it is approaching. That's why we have the absolute value greater than 0. If I didn't have that, then I could substitute 2 into this function and take x is equal to 2, and we don't want that. Okay, so that deals with this portion here. It's the x not equal to 2. Now, let's look at this portion here, absolute value of x minus 2 less than 1. Let's use our rules for absolute values. So this is going to be x minus 2 less than 1, and negative x minus 2 in brackets less than 1, and we solve both of them. And we can basically take an intersection. So it's going to be take 2 over onto the other side, x less than 3, intersection. If you had to solve this, we'll get x minus 2 is greater than minus 1. So x is greater than 1. So we take the intersection between these two, and we're going to get x is between 3 and 1. This one is saying x has to be greater than 1. This one is saying it has to be less than 3. So you combine the two, you're picking a number between 1 and 3 that's greater than 1 and less than 3. Okay, so you combine the two. And look at this. That's exactly what we have up here. Okay, so that's why we have this statement here. So instead of writing this out, this long statement, I can just write it in this form, and it takes care of all my restrictions. What this basically means intuitively is absolute value, you're always looking at a positive. And when you take one number minus another number, you're looking at essentially the difference between the two numbers. But a positive difference between two numbers is the distance between the two numbers. So we are looking at the distance between x and 2, so our x value and 2. And we are saying that distance must be less than 1, but it must also be greater than 0. Greater than 0 because I don't want to look at x is equal to 2 exactly, and less than 1 because look at the values we were looking at, 1 and 3. I chose 1 and 3 from the table. Those are exactly 1 unit away from 2. So 1 plus 1 is 2, 3 minus 1 is 2. They are exactly 1 unit away from 2. Okay, but we aren't looking at 1 and 3. We are saying less than and greater than. So that's why we have the less than 1. Okay, so that's what that portion means. And with that explanation, let's get this all out of the way first. With that explanation, you should be able to write this in absolute value notation as well. Okay, so that is going to be absolute value of f of x minus 5 is less than 2. Okay, and let's solve this. So we have f of x. Let's split that into two portions. F of x minus 5 is less than 2. And we also have the other portion, negative f of x minus 5 is less than 2. Let's get this out of the way first, make some space. Okay, let's solve this one here. Because of 5 there, we're going to have f of x less than 7. And if we had to solve that one, f of x minus 5 greater than minus 2. Take the 5 over onto the other side, we're going to get greater than 3. So you combine them and you get what you started with. F of x has to be greater than 3 and less than 7. Okay, so that's what we have there. F of x between 3 and 7, we can write it as the absolute value of f of x minus 5 less than 2. And it makes sense. This here intuitively means the distance between our y value and 5. Okay, absolute value of a difference of two numbers implies the distance between the two numbers. Okay, so the distance between the y value and 5 is going to be less than 2. And think about it. 3 is 2 units away from 5, and 7 is 2 units away from 5 as well in terms of distance. Okay, but remember, I wasn't considering 3 and 7. There was no equality sign in the inequality. So that's why we have a distance of less than 2 and not equal to 2. Okay, so that's what we have up here. Okay, let's take it out so you can see. Okay, this is what I want you to focus on, that right there. So this brings us, so I want you to possibly write this down on page, and now you're going to look at the next slide and see what we're dealing with. Okay, so this brings us to the formal definition of a limit. So if I have the limit as x approaches a of some function f of x, that's going to be equal to the limit value L. In the above example, we were approaching 2 and our limit value was 5. This here, I can write it in terms of its formal definition. So the distance between our x input value and the value that we are approaching is going to be less than some positive number. And in the previous example, this number was 1. So this symbol here, okay, that was 1 in the previous example. And you know why we have greater than 0? Because we are not considering the case where x is equal to a. If that's the case, if the distance between x and a is less than some positive number, okay, some positive delta, this symbol is delta here, then the y value of the function, the distance between the y value of the function, and the limit value is going to be less than some other value, and this value is epsilon. In the above example, our epsilon was 2. Okay, so that's what it means. That's the formal definition of a limit. If we are some positive distance away from the value that we want to approach, okay, that positive distance is delta. Then the distance between the current y value, we sub in this x value in, and our limit value is going to be less than some positive value, and we call that value epsilon. And that's what I have written out neatly here.